Right. So our next speaker is Jacob Masur, working with Dennis Bondar and Gerard McCall at Tulane. Please go ahead.
Yeah, so thank you for having me. I am, as you said, I work with Dr. Bondar and Dr. McCall, and I will be talking today about why, in a certain sense, all Mott insulators look alike. So the motivation for our research is basically just that the understanding of electron dynamics and electronic properties of materials leads to the development of faster and more efficient electronics. And especially the understanding of these properties on a short time scale is important for that. And the field that studies this is known as ultra-fast physics. And in the modern era, kind of began with the invention of the transistor, which led to microwave electronics and the ability to control gradients on a nano to picosecond timescale. An extra evolution in ultra-fast physics came with the invention of the laser, which gave us ultra-fast optics and the ability to control gradients on a femtosecond timescale. And actually, recently, the Nobel Prize was given to Donna Strickland and Gerard Moreau for chirped pulse amplification. So amplifying these very short pulses to higher power levels. And that was given in 2018, I think. And then the regime that we're currently approaching is known as light wave electronics, which we hope to give us the ability to control gradients on an attosecond timescale. And one of the primary phenomena that's pushing us towards this frontier is known as high harmonic generation. High harmonic generation occurs when a strong field is incident on a material, and that material emits a high frequency response, generally containing multiple like component frequencies. It was first observed in gases, and in gases, high harmonic generation allows us to create trains of attosecond pulses. And since the first observation in gases, it's also been observed in molecules, the surfaces of metals and dielectrics, and bulk crystal. And it's been used within these systems for many applications, like studying the band structure, probing ultra-fast electron dynamics, and studying the lattice structure of these materials as well. And one other material that exhibits high harmonic generation are Mott insulators. And Mott insulators are interesting for a couple of reasons. And one of they became interesting because band theory does a very predict Mott insulators would be conducting, because band theory uses a single active electron approximation. So which ignores the defining characteristic of Mott insulators, which is their strong electron correlations. And these strong electron correlations prevent charge carriers and actually makes them insulating. And it's also the strong electron correlations are the reason that Mott insulators generate high order harmonics as well. They have some useful applications in physics as well. Hole doping Mott insulators has allowed for the creation of Cooper pairs at high temperatures, so high temperature superconductors. And you can also use Mott insulators in a transistor by taking advantage of the Mott insulator to conductor transition. And so this brings us to our question of interest for this talk. So we know that that the high harmonic spectra contain certain information about the electronic properties of materials. But what we're interested in is, does it contain enough to fully understand the electronic properties of materials? And specifically, if we have two Mott insulators and we apply strong fields to both, can we use their high harmonic spectra to distinguish between the electronic properties of these materials? And so we study this using the one-dimensional Hubbard model, Fermi-Hubbard model specifically. And in this model, electrons can hop between nearest neighbor sites with a kinetic energy that is encompassed by this parameter T naught. And electrons located on the same site repel each other with an energy of U. And although this is a relatively simple model, the strong electron correlations that are treated explicitly actually make this very computationally expensive. And it allows for, it means that the two-dimensional Hubbard model is actually a very good benchmark for quantum computers. But anyway, the Hamiltonian for a driven system defined by the Hubbard model is given here in atomic units, where we have h bar is equal to the charge of the electron, which is equal to the Bohr radius and the mass of an electron. So those are all set to 1. The first term in this Hamiltonian is known as the hopping term. It's what allows electrons to hop between sites. And the second term is the on-site interaction term. And the effect of the driving field is just to modify this phase right here. This adds a couple of more parameters to our model that we have to consider when considering electronic properties. But we can, and the phase is specifically the lattice constant A times the vector potential of the field. We can hold, we hold the energy of the incident photons constant. So omega naught stays constant, and we hold the shape of the pulse constant. So the only parameter that ends up affecting the phase that we allow to be modified is what we call the scaling factor, which is the lattice constant times the field strength, F naught. We can also further reduce the degrees of freedom in this system by considering an energy scale in units of T naught, and therefore the ratio of a undriven system can actually, the ratio of the interaction energy to the hopping parameter can uniquely define a system in equilibrium. And so this ratio, if it is about 0, describes a conductor, because electrons will no longer repel on the same site. And when you have any on-site interaction, it generally describes a Mott insulator. And some example spectra for different systems are shown on screen now, and I'm only going to take some time to explain them because they will be important. So we can, the blue plot here is a conductor. We have a value of U equal to 0. And what we see with the conductor is that there are discrete peaks, all centered at odd order harmonics. When we go into a weak Mott insulating regime, this orange plot where we have the ratio of U to T naught is equal to 0.1, we do see some discrete peaks early on, but the spectra is generally more continuous. And then once we get into a strong Mott insulating material, we have basically just a continuous spectra across all harmonics. So this brings us to how we define differences in the responses of these materials. So there are 2 ways that we can theoretically look at the response of a material. There's the time domain response, which is given by the current density expectation. And there is the frequency domain response, which for which we have the power spectra to define the response. You might be asking, why do we look at these both domains? Do they give us the same information? The answer is no. If we when you calculate the power spectra, you take the Fourier transform of the time domain response and then the absolute value squared of that. So you automatically lose the phase information of the response. The full time resolved response will contain at least as much information as the power spectra, if not more. And this is all dependent on how much information is carried about electronic properties in the phase of the response. But the reason we don't just look at the current density expectation is that this is not a experimentally feasible metric. We can't actually obtain the full time resolved response on this time scale. So we use we have our experimentally feasible response with the power spectra, but it does lose some phase information. And so to define, to quantify how distinguishable two materials are, we have defined two cost functions and in each domain. And we have, for both of them, essentially what we're doing is taking the difference between the responses at each time point, or for the power spectra at each frequency, and then we're squaring it and summing overall. And then we take the square root after. This cost function helps us define how distinguishable responses are. So comparisons circled in blue of these two systems indicate low cost response. So highly similar responses. We see here the blue and the orange response are very similar, and will therefore the cost of comparing them in the time domain will be low. And similarly, we have a comparison of these two strong Mott insulators here in the by their power spectra, the cost of comparison will be low also. And then if we and then an example of a high cost would be a comparison, for instance, between this orange time domain response and the green one. So these are considered to be highly distinguishable responses, and therefore incur a large cost. And then similarly in the time domain, we have the conductor plot is highly distinguishable from this orange strong Mott insulator plot. And so before we present numerical results for this study, I want to just give a heuristic understanding of what we expect to see by varying electronic parameters. And so in order to get this, we consider the evolution of the system by the Schrodinger equation. Again, this is in atomic units. And the general solution for the time propagator is given by using, in terms of the time ordering operator, which here is T hat. And sorry, it's kind of confusing. The capital T without a hat is just the period of the pulse. So this is not easy to obtain in general. So what we do instead is we use the Magnus expansion, which gives the solution as a infinite sum, an exponential of an infinite sum. But since we're really going for a heuristic here, we ignore the every term except for the first, and we just use the first order term to give us some idea of what's going to happen. And what we want from this is an effective time-independent Hamiltonian that gives us that will tell us some information about how electronic properties are modified. And so to get that, we just take the integral over the Hamiltonian, and the only time-dependent part of the Hamiltonian is this phase, which is not generally easy to, the integral over which is not generally easy to calculate. However, if you remember the form of phi, we have our scaling factor A F naught times this periodic function, and we take A F naught as an asymptotically large parameter, and using that we can approximate the integral using a stationary phase approximation. And what we get is a effective time-independent Hamiltonian, where T naught ends up being scaled by the inverse square root of the lattice constant times the field strength. And so what this ends up meaning is that, as I mentioned before, the ratio of U to T naught can uniquely define a system. But now that T naught is scaled by the inverse square root of A times F naught, this ratio actually increases by a factor of the square root of A times F naught. What this means is two very different things for conductors compared to insulators. And so just as a reminder, conductors have a value of U that is 0. So we expect to see little change in conductor response as we increase the scaling factor, whereas insulators have non-zero values for U, which means that their responses will be affected greatly by this scaling. And so just a visual representation of this, the power spectra for a conductor, as we saw before, has these discrete peaks. And then Mott insulators have these kind of continuous, these continuous spectra. But as we increase the scaling factor by a factor of 10, what we see is that conductors maintain their discrete peaks on odd order harmonics, whereas all Mott insulators end up coming to this regime where they have continuous spectra. And so this brings us to our numerical results. And so what we've done here is we've taken 100 systems, which are each defined by their own ratio of U to T naught. And we've performed all unique comparisons at these 3 different scalings. Each point on one of these plots represents a comparison between 2 systems, and the cost of comparing them by their power spectra is on the y-axis, whereas the cost comparing them in the time domain is on the x-axis. The red points on this graph indicate insulator to conductor comparisons, whereas blue points indicate comparisons between 2 insulators. And in general, the darker one of these points is, the larger the difference in their electronic properties, which again, at a constant scaling is, and constant T naught is defined only by the difference in the interaction energy. So what we end up seeing from these plots is we have kind of at this, what we call low scaling, all materials are essentially indistinguishable by their power spectra. There is still distinguishability in the time domain for materials that are sufficiently, who have sufficiently distinct electronic properties, but in general, there's no way to distinguish between these materials at low at low scaling. But quickly we see that as we increase this scaling, conductors begin to differentiate themselves. And also, very importantly as well, insulators begin to kind of squeeze down into a smaller region of the bottom left corner, indicating low distinguishability. And then in fact, at high scaling, what we see is that conductors are completely distinguishable by their power spectra. Whereas all insulators are kind of located in the bottom half and of this plot, meaning that it would be very, very difficult to distinguish between any Mott insulator, and hence the name of the talk. All Mott insulators look alike. So what this ends up telling us is a couple things. So first, it tells us that the power spectra is actually a better metric than the full time domain response for distinguishing between distinguishing conductors from insulators, for Mott insulators specifically. And also tells us that access to the time domain is required to distinguish between insulators. At least access to the time domain. Potentially more information is needed, or not more information, but more advanced techniques for distinguishing. And it tells us also that there is a fundamental limit for using these power spectra to identify Mott insulators. So yeah, thank you for listening. I'm happy to answer any questions.
All right, thanks for your talk. Any questions for Jacob? All right. I don't know. Would you like to make any further point, Jacob? Is there a question you would like to be asked that you'd like to ask now? Marguerite raised her hand. Please go ahead, Marguerite.
So can you go back to the slide where you had your response rates for your different insulators? I don't remember yes. Yeah, your dynamic.
Sorry, I gotta go through the animations again. You meant this, yeah?
I think it was the next one. Yes, this one. I'm just curious about the downward trend for the highest U there. Whereas the others seem to be almost trending up slightly. Is there any significance to that?
What do you mean by the? This is actually. Ooh, I messed that one up. Sorry about that. But that is actually the value of U that's U over T naught equal to 1. So we kind of think this is just a result of it being, the least Mott insulating of the materials that are shown. Yeah, I don't really know how much of a significance there is to it kind of decreasing compared to the others.
Okay. Yeah, that was my only question. I just thought I was curious, whereas the others had an upward slope and this one had a downward slope.
Yeah, and then kind of if you extend these, you kind of see that they level out for a while. And I think what I believe ends up happening is these the green and the orange plots, which are strong Mott insulators, kind of reach their peak later in the harmonic order, whereas a lower Mott insulating, a weaker Mott insulator will reach its peak at a lower harmonic order.
Okay, thank you.
All right, any other questions for Jacob? Okay. If they're not, I suggest that we take our lunch break now.